Good evening, my name is Cheng-Hsun, and I'm going to present the paper Semantic Guidance of Dialogue Generation with Reinforcement Learning. The other co-author is Wei-Yun. Nowadays, deep learning has gained popularity in dialogue generation, but its black box-like nature makes it difficult to control. In addition, dialogue generation based on maximum likelihood estimation may result in responses that are irrelevant to the given post. So, in this paper, we came up with an idea to introduce semantic guidance to gain better control of the generated context, and we focused on single-turn dialogue generation. We hope that a generated response will follow the given semantic guidance and also will be correlated to the given post. While implementing current methods to meet our goal, we face some difficulties. The first is that when giving semantic guidance to dialogue generation, the assigned semantic may be repeated or absent. In addition, since the major goal of model is to meet semantic restrictions, the generated response may be dual or unrelated to the given post. To solve the first problem, we implemented reinforcement learning and a specially designed recording system to ensure the desired semantic appears exactly once and does not repeat. As for the second problem, we implemented conditional GAN to ensure the generated response would be diverse and also related to the given post. Let's dive deeper into the detailed methods. We mentioned semantic guidance earlier, but what is the proper semantic guidance? In this paper, we arranged synonyms of a certain keyword as semantic guidance. These synonyms were drawn from knowledge network like YiHaoNet. For example, if we want a generated response to include a concept like tribe, we can find the synonym words ethnic group, and clan in YiHaoNet. These synonyms are then arranged as synonym set or synset and work as semantic guidance in this paper. Later, we try to incorporate synsets into dialogue generation. We implemented semantic condition LSTM, which was proposed by Wen et al. In 2015. An extra vector DT was introduced to the original LSTM to record the information of the assigned dialogue act in the original paper, and we used it to record the assigned synonyms. However, the vector DT still does not guarantee that the desired semantics will appear exactly once, and also, there is no record on the appearance of desired semantics during generation steps. To perform a dynamic recording of desired semantic, we implement an extra dialogue act record cell, or DAR cell. An extra one-hot vector XD is introduced to record the present status of the assigned synonym set during generation process. What should be noticed is that DT records all the synonyms, but SD records only synonym sets because we only want one of the synonym in the same set to appear. Then, how is the vector SD updated? In the beginning of the response generation, we select a certain synonym set and find its corresponding synonyms in D0, which is used to record the information of the assigned synonyms. We also initialize SD as a series of zeros. While generating the response, if any of the synonym appears, we updated the corresponding synonym set in SD. For example, we want the generated sequence to include tribe, and when the word tribe appears at the second generation step, S2 will be updated to have a 1 in the vector. The 1 corresponds to the synonym set of tribe. Now we only record the status of the desired synonym set, but still have not guaranteed it to appear exactly once, and we will fix it later. Up till now, the generated response still lacks diversity and correlation to the given post, so we try to implement sequence scan, which was proposed by Yu et al. In 2017. The sequence scan uses Monte Carlo search and a discriminator to give a score to each generated word during generation steps. The scores then serve as reward for reinforcement learning, which helps the generator to generate sequences that can achieve higher scores. We hope our generated sequence can include the desired semantics and does not repeat. Also, the sequence has to be correlated to the post. Therefore, we change the scoring formula of the original sequence scan. The scoring formula now includes rewards from a sense counter and also a discriminator. The sense counter has the following formula and will be maximized when the desired sense only appears once. As for the discriminator, it contains two LSTM networks and judges the correlation of post and response by reading the post and response in different orders. The final hidden state of the two LSTM networks will then be used to generate reward value of the discriminator. After summing up the reward value from both discriminator and sense counter, the total reward will be implemented in reinforcement learning. Finally, we have achieved our goal to ensure that the desired syntax will appear exactly once, and also the generated response will be diverse and correlated to the given post. Now let's come to the experiment part. In this paper, we chose Weibo conversational data. There were 570,000 post-response pairs for training data and 2,000 pairs for testing data. The testing data was separated to two parts. The first part used semantics that were randomly fetched from real responses to exclude the influence of semantic selection, and was used in both human and automatic evaluation. The second part uses semantics that were randomly fetched from posts to test the feasibility of model in practical scenario, and was used in automatic evaluation. And we chose several methods as baselines for comparison. These baseline models can be modified to incorporate semantic information into sequence generation. We chose sequence-to-sequence with attention, hierarchical gated fusion unit, and semantically conditioned LSTM as baselines, and SER-LSTM with reinforcement learning as our proposed method. In the first part of the experiment, we implemented human evaluation to judge the fluency and relatedness of our generated responses. Here we follow the settings of Sean et al. In 2015, which categorized the responses into suitable, neutral, and unsuitable levels, each with score ranging from 2 to 0 points. And we can see in Table 1 that our proposed method receives the highest score. And we also compare our method with HGFU, which has the second highest score. It turns out that our method also wins with a higher percentage. We also evaluate how our model helps reduce semantic repetition and absence. It turns out that our proposed model with reinforcement learning reaches the lowest semantic repetition and absence rate. We can also notice that STE-LSTM with overgeneration has low semantic repeating and absence percentage, but it gets lower score in human evaluation. Here we also try to evaluate the influence of discriminator in our method. So we have a model trained with a discriminator and another without discriminator. It turns out that a model without discriminator can focus more on reducing repeating and absence of semantics during generation. But the generated sequences are less diverse and also shorter. To automatically evaluate the diversity of our method, we adopt the design of Li et al. In 2016 by introducing unigram, bigram, and trigram. The higher the different grams, the more diverse the generated sequences are. We can state that SELSTM with overgeneration reaches highest diversity, but the diversity is because the generation process is by random selection in this method. And our proposed methods reached great diversity in this evaluation. What should be noticed is that by comparing methods with and without discriminator, we can find that discriminator brings greater diversity to response generation. We also looked up our generated results and found that our proposed method with discriminator generates the most suitable response. In sequence-to-sequence methods, there is no semantic guidance given, and we can say that the generated result is not so fluent. We also can find that with discriminator, the generated response is more diverse and related to the post. Since our semantic guidance is given in synonym set, we hope that when given a synonym set, it can use different words in the sequence generation. And in the example below, we can find that although we choose a certain keyword from a post, it does not directly use the exact keyword in response generation. Instead, it uses the synonyms of the keyword in response generation. In conclusion, we propose SCR-LSTM with reinforcement learning to ensure that our desired semantics only appear once and do not repeat. We also implemented conditional GAN and found that it helped generate more diverse response. Our proposed model also outperforms other baseline methods in human evaluation and achieves lowest repetition and absence of given semantics in generated responses. As for the selection of semantics, we leave it in future work.